Good afternoon, everyone. So, thank you for coming my presentation today. So, my name is Van Tri, come from Computing Architecture. So, today is my final defense for my master's thesis. And about my research, we will conclude about how we can design a secure as function for SHA-3 in system on chip for Society 5.0. So, firstly, we will talk about what is 5.0. So, Society 5.0 is a smart and decentralized network that everything is tried to connect into the network. So, the problem happens when you try to connect every data in one network. It's like everyone gonna see your data, everyone can take your data, so that's why the data security problem is happen. So in that case, we need to protect your data from someone to store it. So in overview, how we can defend the attack from the other. The first, so we can use the message authentication, digital signature, that data encryption, and the final one, the newest one is the blockchain network. And the problem, the main feature is the security hash algorithm can cover all of that application. Like they can use a MAR, they can be a digital signature, they can be a fraud in RSA or something else, that data encryption algorithm, and also they play a very important part in group work. So that the SHA is very important. So now we can go to what is the security hash algorithm. So the SHA is trying to translate a data from a number of various length of the, we call it message, into the numeric string. And the SHA is a one-way function. That means you cannot get a result back when you got the final result. And the SHA family has 3 members. In the family is called the SHA-1, SHA-2, and SHA-3. But in here we just focus on SHA-3. And the SHA-3 is basically a KAGAK algorithm. It has been chosen as SHA-3 by National Institute of Standard and Technology on August 5th, 2015. So the SHA-3 this has more advantage than the older SHA because they have more speed, they lower the hardware resource, and finally they're more security than the older. And by because they're using the new approach technique is called sport function and KAGAK computation. And the motivation about why I need to do it research because in the Society 5.0 they have 4 main demands for that. The first is the speed, because when you try a huge data try to connect into your network, so that's why you need to process all of them. And the other things is the many people want to make their software is more smoother and faster. And another thing is about the comeback system, because the result is more sorted now, so we need to reduce the power. And another things like the mobility, mobile device is very important. Another thing is SHA has many multitask function. And finally, now the software is more very good in their development, so that's why we need this hardware that can cover the software also. And about the related work. So here, I saw that you have 4 related work. The first, about the standalone hardware, they have 3 main things. The first research is a very conventional, very basic design. So it includes we can compare with this because it's the basic one. And the second one is the pipeline with 2 states, and the third one is a new approach with the new control unit. All the things they care about try to improve the better throughput and frequency. But the problem of them is because they are only on hardware, so that's why they just only care for only one SHA-3, SHA-3 256 or SHA-3 510. 12, and they're not flexible because they can only use on hardware. And the other things, the final one I want to compare is SoC design. But the problem with them is like they try the software on that they try only use for they transfer the data only. They don't calculate anything in software, and they have two kind of SoCs hardware design. Is on the first is the conventional one with 24 loop, and the other one is 2 days by light. The problem of them is very slow. So in here, I choose the platform is SoC design because it's very suitable for my demand for the society for 5.0 because they can reduce the cost because they don't need to make many hardware. Instead, they can use many things in there, and they increase the performance rate and also very flexible because they can cooperate between hardware and software together. And I use the Zins Ultra Scale like ZSU 102 for my implementation. About my idea, actually I have 4 main ideas. The first one is used for flexibility and the compact system. So because MC can combine software and hardware together, so that's why I will like rework the algorithm of the SHA-3 so that can be more efficiency for my design. And the 3 other things I will apply for my hardware that can increase and enhance the speed and the throughput to make my system more faster. So firstly, before going to the first methods, I will introduce what is how the SHA-3 work. The SHA-3 work from, you can see they separate into 2 parts. The first is point function and the other the K-cap permutation. The first input, the message going to the testing function, and when they finish, they will put into the absorbing phase, and the absorbing phase will put the data into the K-cap permutation here, and when they finish the K-cap permutation, they will pass the vector data into here and get the data out for the final result. So in this case, before getting there, we will analyze more about the design here. The padding is try to concatenate up to 1,600 bits for the design, and until in the observation phase, they will prepare the 1,600 bits to put into the K-cap permutation, and final one they will try to truncate to get the final design number of output what we need. And the other things like the K-cap permutation, so it's included 24 loops with a basic logic gate, which is you can see here is only AND, SOR, rotate, and NOT. So that's why in here we already want to make this the most efficiency one for my design is I will apply the padding and observing phase in the software. And the other one I will put into the hardware, I will implement on the hardware. And because you need when software and hardware work together, so you need a bridge between them to transfer the data through transfer the data through the software into the hardware. So the DMA, what we call is the direct memory access, is a kind of way. Normally, if someone hardware IP try to take the data from the memory, it will get a command from the CPU, and CPU will get the data from here, and they will take it to the hardware IP. But in the direct memory access, that means the IP will go directly into the memory and take it without any permission from the the CPU. So that's why you can see here they use an SI stream. So that's why it's more faster than the older normal BIO1. And here is the overview of my design. So firstly is the software they will run on the ARM core and store the data in memory in here. And all the things here is implemented on hardware and is run on FPGA. And the data flow will work in here. Firstly, when the software finish, they will store in the memory. And when the data will transfer to the XI and get into the hardware by this way. And the data will get into the data controller. I will talk it later when I will talk about the optimized control methods in the four methods I use this. And when the data get into the controller, and because the SHA-3 core need 1,600 bits to working, so that's why we need input buffer is a 6-bit resistor to concatenate it into, like, stuck it together in 1,600 bits. And then when the starter is finished, so the data will store in the SHA-3 core and like working on. Then when they finish, they will push throughout here. And in this case, because I will talk about on the four methods, because we need we use many types of SHA-3, so that's why we can use this one for increase the frequencies. Next one, I will talk about the SHA-3 core. The SHA-3 core is implemented for the CACAP combination work. So here you can see that the algorithm that's working on the 24-time looping. So instead of 24-time looping, I will replace it with the 24 modules. So that's why I call it fully parallel. So this is the implementation of my architecture. Instead of, like, if we compare with the conventional design, instead of like they need the route, like the looping 24 times, so I will push in 24 modules directly in here to make this more faster and like get more tools. And how the pipeline works, so after like for 24 blocks, the pipeline will fulfill with the data. So in that case, with the 25 cycle, that means the data hash will be the 1 block for 1 hash data. So you can know that instead of 24 for 1 hash, so now we only 1 block for 1 hash. And about how we can use the pre-hash message, the optimized like control selection, what I mentioned before. Because we know when we in SHA-3 they have 3 more options. Like firstly, it's the 256, 384, 512. So doesn't we need some method to like select it more faster? And because normally in if-else it's very slow. And another thing is like when we apply DMA, they can only write and read in 64 bits for 1 clock. And the switch phase, they need because when SHA-3 in CACAP combination, the two root is 1,600 bits. So when they need the 256, they will truncate 1,600 bits to 256. So we need to cut it up, and we will make it go by 2 of these methods. Firstly, I will talk about what is the pre-hash message. So when the data come from DMA into here, so because we're using the software, so we can easily like make the data package into here. So the package include the control package. They will try to like make what is our design SHA-3 output. And the other one is the data package, what we will store in the hash calculator. So how it works? Firstly, you can see the pre-hash get into the data, which is the control. So we can get the number of the 64 bit we can need to store out by DMA accelerator. So, and how we can evaluate my system. Firstly, I will put like I bring everything I working on the PC and to the Vivado software. The Vivo software will and coding and everything will store, and SU will know my code, and they will implement the hardware in this. And the C compiler, as in the SDK, will run my software in there, and the CPU on the SU will understand and run it and get the data into the SHA-3 by FGA. And when it finished, they will store back the data into the SDK and the ILA waveform, and to understand, to get a final result for my verification. And I will use MATLAB to verify all of that data in here. And about the evaluation for my robot design in the FPGA implementation. Firstly, I will compare with the standalone system only. So you can see here, here is the standalone on Vertex 6. It's the equivalent, the technology is the 14 nanometer. So you can see the most important things here, we care about the speed. So that's why our frequency is the best in this list. And the other things, because our throughput is very high, because we can use the fully bilateral system. So that means after 24, the first 24 loop. So that means the cycle only for one pass function. So it boosts my throughput into like 700 something here in the throughput system. So that's why it enhances a lot of throughput to compare with the older and another research. And the other one I will compare is about the SoC architecture design. So the SoC architecture design is about even our frequency is also faster than the normal one, the older one, because we also apply the new robots here, and we also put the software can calculate that. Means hardware is very fast to run all things here, and the throughput is also faster than previous one. And about the ASICs implementation, the first one, so we also apply this on ASIC with the 65 element for SOTP technology by Renesas. So the voltage input is very slow, so you can see only 0.775 voltage. So, and the max frequency we can get is 375 megahertz, and the total power is only 774 megawatts. All thing here is the boss layout simulation. So with a little bit compare here, so our design is also the highest number of throughputs, because we also apply fully bilateral, but maybe the frequency is not the best in this list because it depends on the technology what we have. And finally, it's about the conclusion and the publication. The conclusion of this design is we also just focus on the speed on the SoC system. So we already make the speed is the highest speed in FPGA and on SoC system, and the throughput is totally faster than the older one, because when after 24 clocks, the bilateral is already fulfilled and every throughput is 1 hash 1 clock. And finally, it's very friendly platform with the software. So that's mean because we already apply this for software, so everyone want to use my design, just write the C code or any kind of software system on the design. It will equivalent. And finally, the problem is here, the area is very fast, area large, but the trade-off for that thing is acceptable. So finally, is the reference. Thank you for listening to